Thank you, and good morning. Let's see how this works. There we go. All right, hello, my name is Kevin Newman, and I'm a PhD student at the University of Arizona, where my advisor is Dr. Olivier Guillon, but I end up spending most of my time doing my PhD research at the NASA Ames Research Center, where my advisor is Dr. Ruslan Belikov. So if you're familiar with either of these guys, you probably have some background about what I'm going to talk about today. So together we work on high-performance coronography using the phase-induced amplitude apodization, or the PIAA technique, for directly observing extrasolar planets. So there's several groups that work on PIAA, but for the most part, the development is done with two groups, one of which is the Ames Coronograph Experiment Lab, which is run by Dr. Belikov and is located at the Ames Research Center in California. The other one is the Subaru Coronograph Extreme Adaptive Optics team, which is led by Dr. Guillon, is located in Hilo, Hawaii, and both of these groups have approximately 9 members. Our funding, for the most part, comes from NASA. In the past, this has come in the form of various TDEM and APRA awards. More recently, we are currently being funded as part of the AFTA development, and my funding to be a part of the project comes from a NASA Space Technology Research Fellowship, but I will hopefully be graduating in December of this year, at which point I'll be looking for a job, so if any of you are hiring, let's talk during the break. So what motivates us to develop this technology? Ultimately, it comes down to this. In general, we're interested in directly observing extrasolar planets, but more specifically, our ultimate goal is to find something like this. This is an artist's rendition of an Earth-like planet orbiting around a sun-like star somewhere in our galaxy, hopefully fairly close to us, so that we can potentially go check it out someday. But when we start to discover these planets, we are really touching on a couple of questions that people have been asking in astrophysics for thousands of years now. One of which is, how did life originate here on Earth? And the other is, does life exist anywhere else in our universe? And personally, I think it's really exciting that we sitting in this room here are actually getting to a point where we can start to develop the tools to really answer these questions. So I think that's exciting to be a part of. It's definitely a worthwhile process, and I think it's worth pursuing. So exoplanet science has really taken off over the last couple decades. This is a chart of the planets that have been discovered on a yearly basis over the last couple years, and you can see there's been an exponential increase. The majority of these are attributed to the indirect detection techniques, for the most part transit and radial velocity. And these techniques are great for finding certain kinds of planets, but there are inherently some planets that are not capable of being found with these techniques. So that's where direct detection can somewhat help out. But more interestingly, direct detection is valuable because once you get light directly from the planet itself, you can break it up into what's called a spectra of the planet, and you can check out what is the composition of the atmosphere and then look for signs of potential life on that planet. So this is what a spectrum of some recognizable planets might look like. And specifically, when we're looking for life on a planet, one of the things we're really interested in finding is oxygen. So we are able to do this direct detection using technology called a coronagraph, and the basic concept is that you need to block the light directly from the star in order to see the relatively faint planet which is located close by. This technique is not brand new. Actually, it was used quite a while ago in order to directly observe the corona around our own sun, and thus the term coronograph. The same concept applies to what we're trying to do to observe exoplanets now. we're trying to observe a faint planet next to a bright star, you need to eliminate the starlight in order to be able to see the planet. Otherwise, you're going to be overwhelmed by the extremely bright star. And if we were just talking about geometrical optics, this would be relatively simple. We could just block the starlight and be done with it. However, we have to deal with what's called the diffraction properties of light. When you take an image of a star with a telescope, it ends up looking something like this on a logarithmic scale. And the rings surrounding the central spot are known as diffraction rings, and those are caused by the sharp edges of the telescope, usually the primary mirror. And in most cases, this is actually a good thing to see. It means that your system is well aligned. However, these rings are usually several orders of magnitude brighter than the planet that you're trying to find. So you also need to eliminate these diffraction rings in order to see the planet. Specifically, when you're trying to find an Earth-like planet around a Sun-like star at a distance of 10 parsecs, the difference in amount of light that you see from the planet relative to the star is on the order of 10 billion. And these diffraction rings are still many orders of magnitude brighter than the planet that you're trying to see. So one of the major challenges in coronography is getting rid of the diffraction from the telescope in order to be able to see the planet. The other one is being able to resolve the planet as a separated point source from the star, but this is not quite as much of a challenge because we can build telescopes that are usually able to do that these days, telescopes that are big enough to do that. So the general method that we use for getting rid of those diffraction rings is called apodization. I mentioned that the diffraction rings are caused by the sharp edges of the telescope. So apodization is a process of redistributing the light in the pupil plane and smoothing out those sharp edges so that when you focus the starlight, it comes to a more compact point in comparison, and some of those diffraction rings are eliminated. And this works fairly well. You can think of it kind of like as putting a pair of sunglasses on your telescope, where the outer edges of the lenses of the sunglasses are dimmer than the center, which is almost transparent. And that's one way of reshaping the light distribution in your beam in order to get rid of the rings. This works pretty well, but one of the things it does is eliminate some of the planet light in the process. And remember that the planet is fairly dim to begin with, and any of the photons that we are receiving from the planet need to be conserved in order to do exoplanet science. So a solution that Olivier Guillon came up with is called the PIAA technique. Again, that's phase-induced amplitude apodization. And this is a more efficient method to do the apodization in the pupil plane using aspheric optics. And we can do this with both lenses or mirrors, and the result is that you conserve almost all of the planet light when you are reshaping the beam in the pupil. We have actually fabricated several sets of these optics, both in mirrors and in lenses. You can see more so in the bottom right image is an image of Russ Belikov's eye through one of the lenses, and you can see that it's definitely not your typical spherical lens. It is quite distorted in comparison. So when you do normal original PIAA coronography, you block the starlight once you focus it using something called a focal plane mask, and in the original case, this is just an opaque disk that just physically blocks the starlight. Actually, sometimes you reflect it to another system in the coronagraph to use it for wavefront control. But as far as the coronagraph is concerned, that starlight is now eliminated so that you can see the planet. However, we can actually get better performance sometimes in certain conditions by replacing that focal plane mask with a more complicated, complex focal plane mask. And the concept here is that you provide a phase shift to part of the starlight and then force the phase-shifted starlight to interfere destructively with the unshifted starlight. And when you do that, the destructive interference gets rid of the starlight, and then you can observe the planet. In comparison to PIAA, these designs usually end up having better inner working angle and potentially throughput closer to the star. So of course, PIAA is not the only type of coronagraph that you can choose. There's lots of other proposed designs out there, but PIAA is relatively good performing compared to the other designs. especially when you consider the throughput that it offers by using the aspheric mirror design in the pupil plane for redistributing the light. In fact, some of the PSCMC designs can actually approach the theoretical limit that can be achieved by using direct detection. Another important feature of PIAA is that it can be designed for centrally obscured and segmented apertures, specifically with complex mask. This is important because most of the next generation telescopes that we have coming online now use segmented mirrors in order to have a larger aperture, so it's important that we have a coronagraph design that can be compatible with that. And Olivier has actually published potential designs for all three of these telescopes so far. So I mentioned the complex nature of the focal plane mask for the PIAA complex mask design. One of the challenges that we have in implementing this design is actually making and designing the focal plane mask. That's because the mask is responsible for providing a pi phase shift to half of the starlight, and in doing so, at every wavelength in your observing band. If we were just talking about monochromatic light, this would be fairly easy. We could just have a half wave plate that's sized to cover half of the starlight. That would be pretty simple, but it's important that coronagraphs can operate in broadband, so it's somewhat challenging to design a mask that can provide the phase shift that we need. And that's where my job as the PhD student comes in. I'm responsible for coming up with solutions to this problem and actually implementing them by manufacturing and testing some of the masks that we create. So some of the solutions that we've tried so far include dividing the mask into a series of zones after you pick the material of your mask, and then you can optimize the height of each of those zones to provide a phase shift that is as close as possible to a pi phase shift for half of the light at every wavelength in your observing band. So it's just a big optimization problem wrapped around those factors. If you're interested in having more tools or more parts of your optimization problem that you can use to solve, then you can divide each of those rings into sectors or any other geometry shape that you choose. We started with rings because we wanted something that was circularly symmetric, and our manufacturers told us that they could actually make some of these. More recently, I've been trying to design these masks to have a smooth profile. The motivation for that is that you can have sharp edges at the transitions between some of these zones if they have significantly different heights. And it's an advantage in manufacturing if you can already smooth out those edges in the design so that you don't end up rounding corners that you weren't intending to round. So we have fabricated a couple of these mask designs, more so the original ring type designs. We have two manufacturers for this. The more experienced manufacturer is JPL's Micro Devices Lab. And more recently, we've started a relationship with the Stanford Nanofabrication Facility. Both of these places use a pretty similar technique of starting with some kind of a wafer, usually silicon, adding a layer of resist to the top, and then writing the pattern for the mask that we want into the resist, usually using electron beam lithography, and then transferring that pattern from the resist into the wafer using an etching process. Once we've created the masks and the optics for the whole system, we have a couple different labs that are responsible for testing the systems. I've already mentioned the Ames coronagraph experiment at NASA Ames and Subaru telescope. Both of these systems are in air. The Ames system has a thermally controlled environment, and one advantage of the SCEXAO team is that they can test these systems on sky for the first time at the Subaru telescope. We are also developing PIAA at the Lockheed Martin lab and the high contrast imaging testbed at NASA JPL. And both of these systems are in vacuum for different projects. At HCIT, we're testing the system that we've designed for AFTA. And at Lockheed Martin, we're testing the system that we've designed for the EXCEED mission. Speaking of missions, this technology is being utilized in several different missions that NASA is both in the proposal phase and in various stages of development. I mentioned AFTA and EXCEED. This also applies to XOC, some smaller missions that are being proposed, ASAT, and some future missions such as the new NWT. This is, for the most part, an overview of what I've talked about so far. One new piece of information is that the TRL for PIAA mirrors for unobstructed apertures is around 5, but for the obstructed apertures, the complex masks have not been thoroughly tested as much as their more standard mask counterparts, so the TRL is around 3 for that. So one area for improvement in this region is to actually set up a test bed to test the complex masks with obstructed apertures. So if you're interested in more information about this, check out these awesome publications. And if you have any questions, I'm happy to correspond via email at the address I listed here. So I'll open it up for questions. Some of the more recent results have had on the order of 10 to the minus 8 contrast ratio between 2 to 4 lambda over D, and that's in vacuum in a 10% band, which is an important factor there. At Ames, we've more recently achieved 10 to the minus 7 contrast in air between 1.2 and 2 lambda over D. Theoretically, they can, some of the designs can achieve better than that. It just hasn't been demonstrated yet.
You had made a comment about the broadband limitations. I'm assuming that means the wavelength range that it can work at?
Yes.
So is it currently optimized for, what, 500 nanometers or optical wavelengths? Is there any limitations to lower wavelengths or higher wavelengths?
No, we have designs in both the visible and the near infrared so far. I'm not aware of any designs in the UV, but I'm not sure what the limitations for that would be. But there's not any specific wavelength range that is limiting that I'm aware of.
And so the limit's primarily in the delta lambda, the bandwidth?
Yeah. For the most part, it's making that mask compatible with providing the phase shift that it needs to over a certain range of wavelengths. Usually up to about 20% is the limit we've had so far.
So the silicon mask is going to limit you to something like 1 micron. You can't go shorter than that. Do you have any prospect for using other materials like fused quartz or something to get to shorter wavelengths?
Yeah, so far we've stuck with the materials that our manufacturers are most familiar with. The masks are pretty sensitive to being accurately fabricated to their design, so we've stuck with what our manufacturers already know how to do. One thing that we can use for observing invisible but still using the silicon material is making it reflective. So we just make the mask that we want in silicon and then add some kind of reflective coating to it, and we've already made a couple masks that do that. Okay, thank you.